Without further ado, I'd like to introduce Julie Pepperman, a science teacher in Tennessee's Knox County Schools. She is also a lead and mentor teacher, a member of the state science leadership team, and a professional development specialist. Ms. Pepperman has earned several awards during her career, chief among them the Presidential Award for Excellence in Mathematics and Science Teaching. Ms. Pepperman is a writing team member for the Next Generation Science Standards. Julie, we are so glad to have you here with us today. Let's get started with the presentation.
Good afternoon. I'm excited that you're able to join me, and I welcome you to the Engineering Design Cycle and Physical Science Instruction webinar. As Tim said, I've been a science educator for over 15 years and have had the privilege of teaching in 3 different states in both public and private schools. And as a Presidential Award winner for Excellence in Mathematics and Science Teaching and a writer for the Next Generation Science Standards, I have committed my professional career to improving science instruction. At the conclusion of the presentation, we will have time for questions and answers. So let's get started. We have some goals for our webinar, and since the main focus of this presentation is learning how to incorporate the engineering design cycle into physical science instruction, the goals that we're going to look at consist of understanding the engineering design cycle, comparing engineering design and the scientific method. We want to look at ways that they're similar and ways they're different, how they can complement each other, and considering the link between engineering design, STEM, the Common Core Standard Science Literacy, and the Next Generation Science Standards. And our final goal is incorporating the engineering design cycle in physical science, and we'll actually go through a sample classroom activity that you can use. I don't know if many of you have seen this particular graphic of the engineering design cycle. There are several out there, but the one thing that always impresses me when I see this design is its cyclical nature, and I think that really speaks to what the engineering design cycle is trying to accomplish. We're going to go through each one of these steps or components and discuss what they are, what they mean, and how they can be incorporated into your instruction. We're going to go ahead and start with the ask component, although technically there is no one starting spot. In this component, the problem is identified or the need is identified. We go ahead and look at what research has already been done or is already known, because there's no point in trying to solve a problem that's already been solved. And we clarify the focus of the problem. And in this case, what we're talking about when we try to get students to understand how to develop the ability to ask the right question to research, sometimes with our students they become very, very broad. There's too much information, they're not going to get a good research question. And then other times it's so narrow that there won't be enough information on the topic. So this is an important first step. And it's more than just the students noticing a problem, it's going ahead and doing the research to find out what is already known about the problem. The next component is imagine. In this component, students work in groups, either self-chosen or teacher-chosen, and possible solutions are brainstormed. This is really where they think outside of the box. They can be very creative. We don't want anybody's ideas to be turned down here, because sometimes something that seems very far-fetched ends up being the solution they want to research. All solutions get considered, and then as a group, the students themselves decide on what the best solution is. Of course, they've done the research on the problem already, so they should have some idea of what could be a feasible solution or product. The next component is the plan component. And this is where students have to develop a practical plan. The first 2 components were kind of easy for students. They're used to doing that. But having them develop a practical plan is hard. They don't know a lot of times how to break down their plan into parts, even trying to determine what materials are needed, who's going to be responsible for what parts of their plan, how are they going to develop models and prototypes, who's going to do the drawings, or is there going to be a fee or a cost involved in their materials, and where are the materials going to come from. This is also where students can learn how to set deadlines and accomplish goals and break big tasks down into smaller steps, which, as we all know, for kids in grades 6 through 12 can be pretty challenging. The next part is the fun part. This is where they actually create their solution or their product. They test it. They can test it through many different ways, and of course we want them to be good scientists, so we ask them to test it more than once. This can involve everything. I've seen students do polls. I've also seen students actually create the product if it's something that needs to be used or employed in a particular area, and actually use the product. They've done surveys. They've had other people try the product, and then they collect all this data. They collect the data to analyze whether this was successful or not. The next point after they've gotten all this data is to improve their product. Sometimes students don't get to this point, and that's really doing a disservice to the engineering design cycle. It's really easy to point out to them, in all the products we have out there and all the things we do, you can use a cell phone as a great example. New models come out continuously. They understand the concept of always having to improve something in order to keep it relevant or to keep people interested or to keep people purchasing it. But they don't always get to this step when they do engineering design in the classroom, and it's a very important step because new tests can be run from this step. New data is collected. Then they can do comparison between the new and the old data, and they can continue on, or they might have to go back a step and see if they need to improve their product again. Now, this is one of my favorite things to talk about because for some reason there's a big sense with the educators I've spoken to around the country that you're either for the engineering design cycle and against the scientific method, or vice versa. And in reality, it's not an either-or situation. They can mold perfectly into each other if you really understand the philosophy behind each method. We're going to spend a couple of minutes now talking about engineering design and the scientific method. Scientific method, of course, has been many, many years in the classroom to the point where it's sort of taken on a life of its own. It's become the end-all, be-all of science instruction, almost like it's a content in and of itself, which it's really not. It was a way for students to be taught how to organize their thoughts. The problem with the scientific method is it kind of focuses on just proving or disproving a hypothesis, and there's nothing wrong with that per se, but what happens is students stop right there. A lot of times they think if their hypothesis is disproven, then that means they're wrong or their experiment is wrong and they're going to fail. And of course, we know that's not the case. We want to be able to prove or disprove a hypothesis. But a lot of times they don't have the time in the classroom to go back and either recreate their hypothesis or go through and analyze their results and see why their hypothesis was wrong. Sometimes the scientific method can just be a little bit oversimplified. A lot of times, particularly in the middle school, 6th through 8th grade classrooms, it can be presented as a list of steps that students progress through, and then when they get to the end, that's it, they're done. In reality, in real-world science, that would not be the end. New experiments would be developed, new hypotheses would be developed, new tests would be run, new data would be collected. And the engineering design cycle is also a method of organizing ideas and organizing the process. It has a little bit of a different focus, and the focus is to develop either a solution or a new process or some type of product. And it more typically students really can get into the engineering design cycle because they can see the real-world applications, because this tends to be more how science is done. Together, I view the scientific method as being a way to teach students how to organize their thoughts, and the engineering design as more of the cyclical process of creating and recreating and testing and going back to your idea, brainstorming new things. They're both very important to science, and neither one of them should be taught in isolation. They should always be taught within content. and just a quick comparison of just the steps. The scientific method, you could probably ask 25 different teachers and get 25 different responses to what exactly are the steps of the scientific method. I've chosen this particular set, and as you can see, there's a lot of similarities between the two. The main difference being scientific method is always presented linear with a beginning and with an end, whereas in the engineering design cycle you can see that pretty much at any time you could be anywhere on that continuum and you might need to go back. There's no real ending because there's no real beginning. You're constantly trying to make new strides to go forward. I tend to look at these two as if the answer I receive about my hypothesis in the scientific method can be applied to the research that I'm doing in the engineering design cycle. I see the scientific method as being a component of doing the engineering design cycle correctly. The engineering design cycle is also very valuable because it does support, went too far, it does, I'm sorry, I went one step too far. It does support all three branches of Common Core, STEM, and Next Generation Science Standards. Sometimes some people view the engineering design cycle as something that is separate, and it's not. The engineering design cycle should not be considered something else you have to teach, which brings us to the next slide of how do I fit one more thing into my curriculum. It's not meant to replace or add anything to your current curriculum. It's simply a tool to make instruction purposeful and relevant. When instruction is purposeful and relevant, students gain a deeper level of knowledge. They're able to tie current knowledge or new knowledge to previously learned material, and that's what we want them to do when we bring in those critical thinking skills, is to be able to take knowledge and apply it and use it and create something, to synthesize all that learning into one body of knowledge instead of being all these separate components. The engineering design cycle is the perfect showcase for any school or class that has a STEM focus. And when you implement the engineering design cycle correctly, it can really help you manage the curriculum you are teaching. If you look at some type of project-based outcome and then do a backwards design, the engineering design cycle can be easily incorporated into any unit of study you're doing anywhere from 6th through 12th grade. And if you look at the engineering design cycle as a tool to help you effectively navigate and teach the next generation science standards, the Common Core Science Literacy Standards, or the Science, Technology, Engineering, and Math initiatives, it really becomes very, very valuable. When you apply scientific thinking to actual scientific processes, it can help students gain a deeper understanding. And this shift from standalone information content standards to the union of scientific information and practices is very valuable. Each step of the design cycle calls for action based on information by the use of science and engineering practices that are outlined in the Next Generation Science Standards. Asking questions, defining problems, developing and using models, planning and carrying out investigations, analyzing and interpreting data, using mathematical and computational thinking, constructing explanations and designing solutions, engaging in argument from evidence, and obtaining, evaluating, and communicating information are all practices that are called out in the Next Generation Science Standards as being science and engineering practices that all students should be able to do. The engineering design cycle also supports the first three components of STEM by offering a guiding process to navigate through any type of investigation. And additionally, the design cycle supplies a platform for the application of math to scientific investigations. By its emphasis on research, planning, evidence, and evaluation of information, the design cycle also supports the goals of the Common Core Science Literacy Standards in addition to creating a forum for the utilization of acquired math skills. A lot of the students have a hard time with math, and when you talk to students, they see math and science as two separate things. As science educators, we know especially as they get older and get into high school, math is hand in hand with science. It's part of science. They need to be able to see how what they are doing in math applies to their science research and applies to getting a really good, strong foundation in science education. The next slide will give you an example of a next generation science and a Common Core standard that is supported by the engineering design cycle. This next generation standard is just one I happened to pick. There were many I could have chosen. Is a high school standard. It's physical science, and it's to apply scientific and engineering ideas to design, evaluate, and refine a device that minimizes the force on a macroscopic object during a collision. The Common Core standard is 9th through 10th grade, and it's to conduct short as well as more sustained research projects to answer a question, including a self-generated question, or to solve a problem, narrow or broaden the inquiry where appropriate, synthesize multiple sources on the subject, demonstrating understanding of the subject under investigation. So as you can see, the Common Core and Next Generation also support each other, and the engineering design cycle is a way that you can achieve both of these standards in the classroom. So we're going to look at a sample activity that would apply to both of these standards. And as you can tell by the picture, it's going to involve some football. And if we go back, I chose football because of the macroscopic object, and of course there's a lot of collisions that happen in football. There's the standard again. So in this step, what I would ask my students to do if I was teaching this unit would be to identify the problem or need. And in this case, I might have some articles about recent football injuries, or the player sued against the NFL for concussions, or new legislation that's passed in many different states recently about helmets and concussion safety for high school and college students. You can have the students do some research, and it can either be research that you lead them to, or it can be research that you've given them, and that would depend on the level of your students, how much time is involved, how many days you've planned for this unit, or it can simply be to help focus the question more quickly. So in group, students can do some research on this information you've given them. They can have polls, they can do different quizzes, they can look up any type of media, social media. They can use, I've had students use their Twitter accounts to ask other students, what do you think about the concussion rule? Do you think helmet or any type of concussion safety is an issue? Because I've had students bring up other things like, well, what about soccer where they don't wear helmets but they also have concussions? So this is a really neat area for students because it applies to their daily life. They either go to sporting events, see them on TV, or has a friend who plays in sports if they don't themselves. You always want to make learning as much as possible apply to real life scenarios for them, because then they really internalize what you're trying to do, and it tends to get them more excited and motivated. And the last step here is each group would need to define or identify their particular focus. So here, the group of students, if it's in the beginning of the year, I usually do the selection towards the end of the school year or the end of the semester. A lot of times I will let students choose their own groups, because by this point I know their strengths and weaknesses and I can help them guide. You have students who are good at computer research and students who are good at PowerPoints and doing displays. And you have students who are good writers. You want to get a good mix. You want to have different kinds of kids. If you've ever done group work before, there's always a leader. There's always somebody who's good at making sure we all stay on task. You just want to be aware of that. The older the student is, probably the more you can rely on them to make good choices about their group. Maybe not all the time, but most of the time. And in this particular step, this is where they would be collaborating to brainstorm possible solutions. And when I first introduce this, I tell them, sky's the limit. You don't have to worry about a budget. You don't have to worry about people not liking your idea. This particular step, think of any possible thing that you want that would address or fix your problem or solution. So for example, if the student decided that they wanted to have additional padding in the helmet or a different type of helmet, or I've even had some groups do research on delaying students being able to play in collision type sports like football until they're a certain age, maybe 16 or 17 even, because they did some research that shows that the incidence of concussion goes less once the neck and shoulder muscles are more developed. We've even had students compare concussions in female and male athletes. So it's very exciting for them because I was surprised by the number of students, athletes that I do teach and have taught over the years who have had concussions. After this, we go to the plan stage. This is where they get bogged down. This is really where, as a teacher, as a facilitator, you need to be moving around and making sure that people are staying, they understand what you mean by a plan. The good news is once you've done a few engineering design type activities incorporated into your content, students start to understand what you want. They know what you're looking for. So in the beginning, I usually start out with the engineering design cycle as very teacher-led, very focused, very guided type inquiry. And by the end, I'm basically in the background to offer support and answer questions, but they're running with this. Because that's how it is in college, and that's how it is in the real world. People work in groups. They're expected to be responsible. They're expected to be able to get the job done, and that's where we want these students to be. We want them to be college and career ready. So in this area, students have to provide me with proof of their plan, and it's usually, some kids have done timelines. I've gotten, in my honors classes, actually written proposals where they've even broken down estimated cost, estimated time, where they'll get materials. They've had nice glossy covers. They went all out. I've had students achieve this particular part of the engineering design cycle simply through some type of PowerPoint where they've gone through and everybody's assigned. It kind of depends on the group and what types of kids are in the group, whether they're more visual and they like graphics and images, or whether they like to write and type things out. They're also going to have to figure out how they're going to build their prototype here. Usually in the plan stage, if it's a bigger group or I'd say a more complex project, you can actually have subgroups within the larger group. In this step here, the create step, the solution product is actually created and tested by the students. At first, the students, especially if it's complex like making a football helmet, they get a little discouraged because they want to actually make the helmet. And a lot of times when you're doing this in your classroom, you don't have the resources or the access to that type of material. So the students have to improvise, and that's fine. The idea is not so much that we're going to take this product and actually go get it developed, although that would be wonderful if they could do that. The idea is the process behind doing this. So as long as they can create a prototype that can be tested, that's fine. When they're testing the prototype, in the beginning I've had students just test it with each other. But as we've gotten bigger and longer and more complex engineering design projects, we've had students have to go test it with the rest of the student body. I've had students go to the local mall and ask people to come up and test it. Of course, we had an adult with them. I've had students send out survey monkeys and quizzes and all these different things to get data. For me, as a teacher and a facilitator, there has to be enough data. I'm trying to get students to understand that just doing a test one time or just having 5 people test the product is not going to give you accurate and reliable data is kind of hard. They do eventually get it, but it does take a little while. After their data, this is the part the kids really like. At first they get frustrated, though, I'll admit that. When they develop something and they're proud of it, it bothers them when they get data back saying, well, no, other people didn't like it, or it did not work, or your design was faulty, or your research was faulty. Sometimes they take it a little personally and they get offended. You have to walk them through that. You have to let them understand that it's not a personal thing, because kids at that age tend to take anything negative as personal. You have to get them to understand that this is what happens in the real world. This is how businesses, when their research and development departments make something, this is what they do. Sometimes I'll go through a little slideshow I have with the students on products that companies have put out and failed. It's usually pretty humorous. Sometimes they're surprised by some of the things that big companies that they think are always successful, like a McDonald's or a cellular phone, that they always come out with something that works. And they don't. Products quietly die and go away. We can also take it to the next level and talk about the search for new medicines to help with different health conditions, and how some work and some don't, and some had to be removed from the market. You're kind of trying to get the kids to think on a global level here. So when we go back to this step where we have to improve our design or our product, they need to do it based on their data. It can't be based so much on their feelings, but on their data and what feedback they've gotten. Depending on how much needs to be done in the improve step, of course, influences where you go from there. You can continually go backwards and forwards and backwards and forwards on this engineering design cycle, especially if it's a large enough product and the kids are a solution and the kids are dedicated enough to it and they really, really want to keep refining it. After the product is created and they think they've improved it, sometimes after a couple weeks of doing something else, I'll go back to that product or that solution and I'll say, do you think there's anything else you could have done? And that really gets them thinking, because like most kids, when they finish something, they just want to be done with it. And the whole idea here is not so much to keep frustrating them, although that is fun. The idea is for them to constantly be asking questions, not only of the material they're learning in school, but of the things they're creating, the things they're learning. We want them to always be looking for more information and to delve deeper into their content. So, in conclusion, the engineering design cycle is a wonderful tool for engaging students in the practice of science in the same way scientists and engineers practice science. The design cycle gives students the opportunity to act like scientists or engineers and learn science through the application of all that content we've been teaching them: research skills, writing, and math skills. The design cycle also supports learning in context and can be easily adapted to many areas of science. And we designed this webinar to go about 30 minutes and to have the rest of the time for questions and discussion. So I am open to any questions that you might have.
Thank you, Judy. We do have a couple things coming in. It says, do you have a list of other problem-based projects for physical science?
I do not have a list. I can get a list. I can just go through my curriculum materials that I use and develop one if somebody would like that.
Okay. Another question just came in. Steve asked, how did your students test football helmets?
They used football helmets that they already had. They got some from the high school football team. This was a 9th grade class. And they simply hit them with hammers and looked for cracks. We were trying to judge. They had an egg, an uncooked egg on the inside of the helmet, and it was taped to the top of the helmet from the inside. And they used a regular, I guess it's a sheetrock hammer, and they hit the top of the helmet, and they calculated how many hits it would take, or if the egg would crack, and if it did crack, how many hits did it take. And that was one of the ways, and that was a grade level to average to a little bit below average students who are doing that particular project. Did I answer your question?
Mm-hmm. Thank you. Denise asks, do you have resources to support elementary engineering?
I do have resources. I did not talk about elementary in this particular webinar because we developed it for 6 through 12, but I definitely do as a professional development specialist. I have also had to work with first through 5th grade in engineering design. We do it in kindergarten also, but it looks a little bit differently. It's much shorter, just like 1 day to maybe a day and a half of things. But yes, I do.
Thank you. Another question just came in and says, what do you think about projects offered in Active Physics book by Eisencraft?
I use some of Eisencraft's stuff. The whole point with the engineering design cycle, though, is it is new for students. And the state of Tennessee has had engineering design as part of its standards for a couple of years, and so has, I believe, Massachusetts. But it was sort of taught as a standalone and not so much within the content. And my goal, and some of the other teachers in my state and with NGSS, has been to get people to see it as a way to teach content and not a separate thing. So we haven't gotten to the point in a lot of our schools in Tennessee, East Tennessee actually, where the students are doing these massively big, complex projects simply because a lot of students don't even know what the engineering design cycle is until we started working with it. It definitely is a process of teaching them what you expect, teaching them the components, and you should always be doing it with some type of content. But I do love the Active Physics series.
Okay. Denise asks, where did I wonder if she might be meaning, where can I find the elementary engineering resources that you were mentioning?
The elementary engineering resources I use are just things I've developed or found on the internet or gotten from other textbooks. There's no one place. You can usually do a fairly good Google search for engineering design in the elementary classroom. They'll at least get you started in the right direction. Sorry.
Oh, no, thank you. Sandy asks, how much class time do you give towards each engineering design cycle assignment?
It depends. And this is the biggest problem I had when I started really teaching the engineering design cycle was class time, because we have a pacing guide and a curriculum that we're expected to get through before our state testing. So I was very nervous about giving up class time to do this engineering design because I hadn't actually wrapped my mind around the fact that it's not supposed to be separate. Once I started seeing it from more of a project-based type of teaching instead of something I'm teaching separately, I was able to incorporate quite a few of my standards within any given project that I choose. And obviously I'm choosing the projects because I need to make sure the kids stay within a certain parameter for my course. But once I kind of changed my mindset and saw how they would learn their content through participating in the engineering design, then it really didn't matter because I didn't look in class time as much as I looked at, well, we're working on this standard and it goes right in here to the engineering design. You do have to, as a facilitator, especially when they get really stronger skills in being able to work through the design, you do have to make sure that you're staying on top of the kids as far as, is one kid doing all the work, is the other kid sitting back, are they all getting the same content? And to that end, you can develop little quizzes they can take. You can divide it into modules to where, well, you can't go on in the engineering design cycle for this project you're on until you pass or complete this quiz, this test, this essay, and the essay will be on the content and not on the engineering design. And that'll give you some really good feedback about who's learning what, how far are they. It's sort of like almost like a flipped classroom.
Thank you. Alicia asks, what would you recommend for a teacher who would like to start EDC for the first time in a middle school classroom? Where should I start?
One of the cool lessons out there that you can use to start with is sort of the evolution of the cell phone, because obviously they're fairly modern, but kids really think cell phones didn't start until the 2000s. Obviously nothing good happened before the year 2000 to them, but when they see some of the old bag phones, the mobile phones, the car phones, they're really surprised and impressed. And when you show them that picture of, I think it was 1979 or something, the Motorola, the giant phone, then they start to get an idea, because that is something that, whether they have a cell phone or not, they're inundated with cell phones, their friends have cell phones, and they see the constant advertising of the brand new iPhone, the brand new Samsung Galaxy. That is something that is very relevant and they can relate to very easily. So what you can do with some of those kids is have them look at some cell phone cases. You know, talk about the cell phones, and that can also bring into your curriculum some of the communications. In my particular curriculum, we have some communication standards we have to teach, but it can bring that into it, and then you can look at the cell phone cases, and you can have them create or design their own cases and to improve the cases that are out there. I've had kids design them out of cardboard, duct tape with padding to protect their phone, because they're constantly dropping their phones and cracking the glass, so they're always thinking of ways to protect their phones. But it's a nice little introduction to using the engineering design cycle, and it's something you can do, I'd say, with 6th through 9th grade, probably within the first week or so of school. It's a nice little introduction and gives them a taste that your class is going to be a hands-on, and those kids are expected to be full participants.
Thank you. Steve asks, how do you assess the group projects, especially if different students are putting in different amounts of work?
That's always a problem when you have group work. It doesn't matter what you're trying to accomplish. You always have that go-getter kid who either is terrified no one else can do the project correctly, so he's going to do it himself, or he just is very gung-ho and excited about the project. And using the modules I was talking about, where you divide your content into modules, at least you can tell that they're doing the content. But also, when the kids are doing this, you know, you have to be active. You have to be walking around. You have to be listening to who's speaking and who's doing what. You can have checkpoints in the very beginning set up to where